Hello everybody and welcome to this GCSE Chemistry video about rates of reaction. We're going to do a question walkthrough today, so what I'm going to do is I'm going to show you some GCSE questions and I'm going to model my thoughts out loud, and I'll use blue to model my thoughts, and then when I'm actually writing down the answers that get you the marks, I will write those in green, so you'll be able to tell the difference between reasoning and the actual answers. Okay, so in this question we are looking at an experiment and a description of that experiment. And so what they're saying is we're looking at magnesium reacting with dilute hydrochloric acid, and from the chemical changes topic you'll know that that produces hydrogen gas. And so what they're doing is they're taking 50 cubic centimetres of the hydrochloric acid, adding 0.2 grams of magnesium ribbon to it, and they're attaching a gas syringe to the conical flask to collect the gas, and they are measuring the volume every 10 seconds. And we've been presented with a graph of their results, very common to have a graph question. And you can see that the volume goes up, starts to level out, and then is completely flat at the very end of the journey. And so our question is asking us to calculate the mean rate of the reaction in the first 10 seconds. So mean is one of the averages that you can be asked to calculate. And so we've been told that we need to look for the volume of gas produced after 10 seconds. So 10 seconds on the x-axis is here. And so if we zoom in very briefly on this, we will see that at 10 seconds we are here. And so that is halfway between the 8th and the 9th line, which means this is going to be 17 cubic centimetres of gas. And then that, of course, has taken 10 seconds. And so what we need to do then is take our 17 for the cubic centimetres of gas and divide it by 10, and that gets us a mean rate of reaction of 1.7. And the units for this, because we had cubic centimetres on the y-axis and seconds on the x-axis, will be cubic centimetres per second. And that actually is the answer to part B. So that's why I've put the lettering in blue for part A, because actually we need it for this second section. And just to explain those units again, we have got cubic centimetres on the y-axis, and we're dividing it by seconds, and so it is literally cubic centimetres divided by seconds, and that's why this is the correct answer. For the second units, we would need to have a mass on the y-axis, and that would be grams per second. This third one is just a complete decoy, as is the fourth one. You will never have the time first in any set of rate of reactions units. This second one is kind of like reasonable, but it's not the right answer. And then the final question on this page says, give two conclusions that you could make about the rate of reaction, or about the reaction, I should say, between 90 seconds and 120 seconds. So that is this section of the graph here. And so I will write my answer in that section. So first up, the rate of reaction can be deduced from the gradient of the line. This line is flat, and so the rate of reaction is 0. And what that means is, so I'll bullet point these, the reaction has finished. And we know that the reaction has finished because no more gas is produced. And we can even show off here that no more gas is being produced because one of the reactants has been used up. And that's why the reaction has stopped. And then let's just take a quick look at the number of marks. There's only 2 marks available here, so we wouldn't be expected to put all 4 of those. We would just pick 2. And I would say that I think the first 2 probably is the best, but you'll get 1 mark for each of those bullet points. So we're still on the same question here, and the student has repeated the experiment, only this time they have used magnesium powder instead of magnesium ribbon. So magnesium ribbon is a thin piece of magnesium that you might have burnt in a Bunsen burner, and the powder is of course that ribbon that's been chopped and then ground up into really fine pieces. And what is the independent variable in this investigation? So the independent variable is the one that you change. And just to contrast that, this is not part of the question, but the dependent variable is the one that is measured. So the result that you measure, not just any quantity that you measure, but the actual result. And then the control variables, those are the ones that you keep the same in an investigation. But we're being asked about what we're changing. And by taking the ribbon and crushing it up and grinding it up really small into a powder, what we are changing is the surface area of the magnesium. And just to explain the other variables, the temperature of the reaction, that would be a control variable. The volume of gas that we are collecting, well, that is our final result, so that is our dependent variable. And the volume of hydrochloric acid that goes in the container, well, that would be another control variable. And the final part of this question, sketch a line on the graph to show the expected results of the experiment using magnesium powder. Well, so there's two parts to this. First of all, we've got the height. The final height that this graph goes to, that depends on the quantity of reactant used. If we use the same quantity of reactant, we will get the same height. And we have used the same quantity of reactant. The only thing that we've changed is the fact that it is a powder. And so that means that our final height needs to be the same. And that will get us 1 mark for this answer. And then the next thing that we need to consider is we need to consider the gradient of our line. The steeper the gradient, the faster the rate of the reaction. And in this case, because we're using a powder, we would expect it to be a faster rate of reaction because we've got that higher surface area. And so there's no actual kind of like precise gradient that we need. It just needs to be steeper than the original line, as I've shown there. And obviously it needs to be connected in the two, but what they will specifically be looking for is how steep that line is and how high it goes at the end. And then it just needs to be connected between the 2 points. This next question is about one of the practicals that is really common to come up in a rates of reaction question, and that is called the disappearing cross experiment. And you can use this to investigate the effect of concentration on a rate of reaction, which is what has happened here, but equally you could use the same method to change the temperature and vary that from one experiment to the next. And so we've got this experiment where we're being told that we form a cloudy solution. And what happens is we take 50 cubic centimetres of sodium thiosulfate into a container. And we can see this container down at the bottom. This container is in fact a conical flask. And we put the container on a cross drawn on a piece of paper, as you can see from the left-hand side of the picture. And then we add some hydrochloric acid to the mixture and we start timing using a stopwatch or a stop clock. Then we stop the timing when the cross can no longer be seen. And you can see this person is looking down through the top of the conical flask. And then we record the time taken once that cloudiness has obscured the cross. And so I say it's called a disappearing cross. The cross, of course, doesn't disappear, but we've made so much of the cloudiness that that cross can no longer be seen. And then we repeat this experiment for steps 1 to 5 with different concentrations of sodium thiosulfate. And that is the independent variable on this occasion. And so what we would have to do is we would have to keep temperature the same in this experiment. And I think that's coming up, but that should be going through our minds. And if we were changing the temperature, we would of course be keeping the concentrations the same. And then we can see the equation for this reaction with words and also with state symbols. And then the question says, why does this reaction go cloudy? And that comes from the state symbol on the right-hand side. This is the only substance that has been made as a solid. And so we've been given tons of space, but we don't need all that much space. We produce sulfur, that would get us 1 mark, which is a solid, which would get us a 2nd mark. We could really show off, and we could call it a precipitate. And precipitate is a slightly more technical word for the insoluble solid that is produced during a chemical reaction. So, following on from the same question, the student measured the volume of hydrochloric acid with a measuring cylinder, and we're being asked what apparatus can be used to measure the volume more accurately. Now, the first one is the actual right answer here. Pipettes are brilliant methods of measuring really precise volumes, really accurate volumes. And that's because they've got one line only. And if you get the liquid up to that line, you have got precisely the volume that you're seeking, whether that's 10, 25 or 50, which is the case in this instance. Now, the next answer, beaker, is a complete decoy. You would never ever measure volumes with a beaker. They have maybe maximum 4 or 5 measurements on the side, 150, 150, 200 and 250 perhaps is typical, but that is very, very inaccurate, and so you would never use a beaker to measure volume. Test tubes don't even have any measurements on the side, so hopefully nobody thought test tube was the right answer, and ruler is definitely not for measuring volumes, it's for measuring lengths. Next, give 2 variables that the student must control to make this investigation a fair test. Now, I have just said that temperature would need to be one of them because that can have a huge impact on the rate of the reaction. And so that would probably be the first thing that I would say. But other things that we'd need to say are the volume of the sodium thiosulfate, because that would make a huge difference on the rate of the reaction, and the volume of the other chemical as well, so the volume of the hydrochloric acid. Now, since it was the concentration of sodium thiosulfate that we were changing, we can't say that that is a control variable for the fair test, but we could say the concentration of hydrochloric acid. That would be absolutely fine and a very important one to keep the same. So any 2 of those would be what we are looking for. The next question asks us to calculate the mean from this results table for the 0.08 moles per cubic decimeter concentration of sodium thiosulfate. So you can see the 3 concentration values, and it looks like they repeated the experiment 3 times for each different concentration. So we've been asked to calculate the mean. So there's 2 marks here, which is at face value quite generous for a mean, because if you remember what you do for a mean is you add up all of the numbers to get a total and divide by the number of numbers. And so if you were to add up those 3 numbers, you would get a number that you could divide by 3 and you'd get 1 mark for your efforts. What you have to spot is that 41 is quite a lot bigger than the other 2 for this concentration, and it's actually closer to some of the numbers in the previous row, and so this is an anomaly. And so the anomaly needs to be left out of this experiment calculation, and so we need to simply do 31 plus 33, which gets us 64. We need to divide that number by 2, which gets us our answer, which gets us the mark of 32. There would be 1 mark for spotting and leaving out the anomaly, possibly 1 mark for the calculation. If you didn't leave out the anomaly, you would get 1 mark, but 32 is the correct answer. And finally, suggest why the student might get unexpected results. Now, this is down to one of 2 things. First of all, they might not have controlled their control variables properly, or they might have done something in their method that is inadvisable in terms of achieving accurate results. So, for instance, if they use the same measuring cylinder for both of their different chemicals, then this would lead to a very, very odd result. And this is, of course, going to lead to an anomaly. Alternatively, they might have not used the same cross each time. So if they had a different cross and maybe one of them was really small cross and one of them was an absolutely massive cross, well, obviously it would take a lot more of that sulfur to produce the cloudiness that meant that the cross was obscured. Now, we could also have maybe had a timer delay. And so what I mean by that is perhaps the person's reaction times were different. So they added their second chemical, the acid, and maybe they waited a moment and then went, oh gosh, I need to start the timer. And there was that time lapse. And so that might be why the experiment was taking longer than they would think. This question is about indigestion tablets which contain the chemical calcium carbonate as their main active ingredient, and in this occasion it says the only active ingredient, but that simplifies it for our question. And we're told that calcium carbonate neutralises some of the hydrochloric acid in our stomach. Two different indigestion tablets, X and Y, were separately reacted with excess. That means we've got more than enough, so we've got plenty. That will not be the chemical that's going to run out. So there's an excess of hydrochloric acid. The volume of gas given out, which we should know is carbon dioxide. When a carbonate reacts with acid, we make carbon dioxide gas that turns lime water cloudy, and it was measured every minute to find out what volume of gas had been produced. And you can see that we've got two lines. The line X finishes here and begins with this steep line. I'll just make it a little bit easier to see. So this is line X. And line Y is the dashed line that's a little bit easier to see, and that finishes higher but isn't as steep. So which tablet X and Y contained the most calcium carbonate? Now remember, this is like question 1, where we said the height that it ends up is determined by how much reactant we use. And so the answer to this question for the first part, it's only a 1-mark question, so we can't be getting a mark for saying Y. And so the explain the reason for your answer has to be part of that same mark. And so it's a very simple additional answer, but we need to say that more gas was given off, or more carbon dioxide, if we want to show off. And then for the second part of the question, which tablet X or Y reacted faster with the hydrochloric acid? Now this time, this is going to be X. And the reason is that the curve, or the slope, or the gradient, whatever word you want to say, is steeper. And so remember, the steeper the line, the faster the reaction. The higher the line, the more product you made, which must mean the more reactant that we had. Then it says explain the shape of the graph between 3 and 5 minutes. And in fact, this is exactly the same as what we've said previously, because we're looking at curve X. And between 3 and 5 minutes, this reaction has finished. And so that's because the calcium carbonate, I think we do need to personalise it on this occasion, because we were told that the acid was present in excess. So the calcium carbonate is used up. And this is only 1 mark, so that would be all that we need to say. And we could still say that the reaction has stopped, and that would get us the same 1 mark. The final question that we're going to look at here is about the same reaction, calcium carbonate reacting with hydrochloric acid. This time we have been shown the equation, and we've been told that we can be studying the rate of this reaction by again measuring the amount, volume, of carbon dioxide that is produced. This time it looks like 4 experiments have been done, which have been numbered 1 to 4. In each experiment, the amount of calcium carbonate, the volume of the acid, and the concentration of the acid were kept the same. These are control variables, but the temperature of the acid was changed each time. So that is our independent variable, different temperatures of the acid each time. And we've been told that the calcium carbonate was in the form of small lumps of marble chips. So small pieces like so. And we've been given our graph. So apart from altering the temperature, suggest 2 ways in which the reaction of calcium carbonate and hydrochloric acid could be speeded up. So we could go for adding a catalyst, and a catalyst will always speed up the rate of a reaction without being used up itself. Or we could increase the surface area, and that's like the magnesium question, where we could chop it up into smaller pieces or use a powder. And the final one is we could increase the concentration of the acid that is being used. And the reason that we can do those things, or the reason that we should think to do those things, is that these are the control variables that were mentioned earlier. So the temperature was the thing that was changed, but the control variables are the things that need to be kept the same. Next, it says which graph 1 to 4 shows the results of the experiment in which the acid has the highest temperature. And so the highest temperature is the one that you would expect to be the fastest reaction. And looking at this, we can see the gradient, how steep this line is. 4 is the least steep, 3 is a bit steeper, 2 is a little bit steeper, and 1 is the steepest. And so we would expect the answer to be experiment 1, which might well get us that mark, because there's 2 marks available here, unlike on the previous question when there was only 1. So experiment 1 is the fastest, and so it makes gas the quickest. And we can tell it makes gas the quickest because if you were to stop and sort of inspect how much gas had been made after, say, 1 minute, well, not very much, less than 10, about 10, maybe about 15, more than 30. So experiment 1 has clearly made gas the quickest. And then part C, or C part 1, in experiment 2, how does the rate of reaction after 1 minute compare with the rate of reaction after 2 minutes? So we're looking at experiment 2. So at 2 minutes, it's here, and at 1 minute, it's here. So the rate of reaction is how steep the curve is. So at 2 minutes, the curve, if we draw a tangent to the curve, that is approximately how steep the curve is at that point. Whereas after 1 minute, it's that steep. And you can see that that is steeper. And so we need to say, it's only 1 mark, we need to say it is faster at or after 1 minute, or slower at 2 minutes. And that's literally just to do with the gradient of the line. And then the final question says to explain as fully as you can why the reaction rate changes during the experiment. Now they've actually asked us to look at experiment 2 here, but we could be looking at any of these 4 reactions because the answer is the same. So I think it's a little bit sneaky of them, maybe a bit misleading to say experiment 2, because they all follow the same pattern. They're really fast, they start to slow down, and then they stop. Experiment 2, it's really fast, starts to slow down, and then it stops. You get the idea. So what we need to say, so that would be a description though. So we've been asked to explain, so we need to give the reasons for the description. And so we've got 2 marks here. So we need to say first and foremost that the reactants get used up. That would get us our first mark. And so because they get used up, their concentration of reactant goes down. And because the concentration of the reactant has gone down, the collisions between reactant particles will be less frequent. And so that frequency of collisions is everything in terms of the rate of reaction. And so if I just point to this point here, say on reaction 1, the collisions must be far less frequent than they were down here because the rate of reaction is producing far less gas in the same amount of time. And so the collisions between the reactants must be less frequent. And in fact, for showing off, we could say the word successful collisions between the reactants is less frequent. And that really, that third bullet point, because there's only 2 marks for this question, and so if it was me, I would say the first one and the third one. The reactants get used up, so the successful collisions between reactant particles is less frequent. Okay then, that's the end of these questions. I hope you found it useful. I'll see you again soon. Thanks. Bye-bye.